Hello everyone, let us continue our discussion of the preliminaries. In this video, we take a close look at convex functions. We begin with defining convex functions. As we mentioned earlier, we will only be dealing with proper closed functions. Recall that a function is proper if its domain is non-empty and the function value is not minus infinity anywhere. On the other hand, a function is closed if its epigraph is closed. In the same way, a proper closed function is convex if and only if its epigraph is a convex set. So we have defined closed and convex functions only by using properties of their epigraphs. Just a remark that you have seen the terms closed and convex applied to both sets and functions now. We are essentially overloading these terms because they actually mean different things when they are being applied to a set or when they are being applied to a function. Usually we do not say explicitly if a particular usage is for a set or a function, but it should be clear from the context. So when we say that the function is closed and convex, if its epigraph is closed and convex, we are actually using two different meanings in the same sentence. Please take a moment to appreciate this and try not to get confused with the usage. Let us take a closer look at this definition. Recall that to check if a function is convex, we would need 2 points x and y in the set and then draw a line segment between those points. If the line segment lies inside the set, then the set is convex. So if we apply the same definition to the epigraph, we would actually get a corresponding condition on the function f. So please verify that the line segment condition applied to the epigraph leads to a zeroth order condition on f, which says that f of theta x plus 1 minus theta y is less than or equal to theta f of x plus 1 minus theta f of y for all x and y in the domain of f and theta between 0 and 1. In other words, the zeroth order condition is a direct consequence of the epigraph of f being convex. If this was the first course in convex optimization, you would probably not see the definition of epigraph till later. But here we are starting with this epigraph based definition so that you are able to build intuition on the basis of what you already know. Further, the epigraph based check for convexity is not an academic exercise. In contrast, it will prove to be immensely useful in a wide variety of examples and settings. For instance, consider the indicator function of a closed convex set, calligraphic x. Recall that the indicator function is an extended real valued function that takes the value 0 when x is in calligraphic x and infinity otherwise. Also recall that we derived the epigraph of the indicator function of calligraphic x in the last video, and it turned out to be the set of all x, t such that x was in calligraphic x and t was non-negative. In other words, the epigraph of the indicator function of calligraphic x was the set calligraphic x cross r+. Now since calligraphic x is given to be closed and convex, and further r+ is also closed and convex, the epigraph is also closed and convex. Hence we conclude that the indicator function is a closed and convex function. So in this example, we directly applied the epigraph definition. You can of course verify it using other definitions. So while the indicator function looks a bit odd, the fact that indicator function is closed and convex will be very useful later on, as it will allow us to define its subgradient and use it in the algorithms. Another example is the norm function. Again, recall that we have seen the epigraph of the norm function, which is the set of all x, t such that norm of x is less than or equal to t, which is essentially the definition of the norm cone. So the epigraph of the norm is the norm cone, and we have already seen that the norm cone is a closed and convex set. Hence we conclude that norm is a closed and convex function. Note that you can also verify that norm is convex from the zeroth order condition by using the triangle inequality and the homogeneity properties of the norm function. Please do verify that the zeroth order condition holds for any norm. As before, because semi-norm cones are also closed and convex, we can therefore conclude that semi-norms are also closed and convex. When dealing with continuous functions, there are more useful definitions that we can generally apply. For instance, if f is differentiable, then we have the first order condition, which says that f of y is greater than or equal to f of x plus inner product of gradient f of x times y minus x. The first order condition can actually be modified to allow non-differentiable functions as well. In that case, we would have the subgradient of f at x, We will later show that you can always find the subgradient of a proper closed convex function. So the first order condition is very general and will apply for all proper closed functions. However, this general first order condition is not very useful when checking if a function is convex or not. If f is twice differentiable, then we have the second order condition which says that Hessian of f at x is PSD for all x in the domain of f. This definition cannot be extended to non-differentiable functions, however, so it is not so general. It is therefore only useful for sufficiently regular functions. Further, there are only some situations where the Hessian can be shown to be PSD analytically for all x. A simple example is the quadratic function. You can evaluate its Hessian with respect to x, provided you know the basic rules of vector calculus. If not, please go through the vector calculus rules. The Hessian of the quadratic function x transpose qx turns out to be 2 times q. Therefore, the quadratic function is convex whenever q is PSD. Consider another example in R2 where f of x, y is equal to x square by y with domain of f equal to r cross r plus plus. That is, x can be anything but y is required to be strictly positive. Note that for all x and y outside the domain of f, we can define f to be infinity as usual. The Hessian of f over any point that is in its domain can again be easily calculated. You can verify for yourself that Hessian is given by 2 by y times the matrix with entries 1 minus x by y, minus x by y, and x square by y square. So how to verify that if this matrix is PSD or not? One way is to try and factorize the matrix. In this case, the matrix can be written as the product of the vector 1 minus x by y with its transpose, which is PSD. This is because whenever you can factorize a matrix as L transpose for matrix L of any dimension, then such a matrix is PSD. We can in fact verify that this is the case by trying to calculate U transpose AU for arbitrary U. Substituting A is equal to L transpose, we obtain the L2 norm squared of vector Lu, which is a norm and therefore always greater than or equal to 0. Hence U transpose AU is greater than or equal to 0 for all U, implying that A is always PSD. This property that any PSD matrix can be factorized in this way is very useful, particularly when trying to verify the second order convexity condition. There are many more examples of functions that can be verified to be convex by using the second order condition. If you have done a first course on convex optimization, you must have gone through them. Otherwise, you can practice them on your own. Next, an important example is the pointwise supremum operation. Consider a function f of x, y, which is given to be closed and convex in x for each y belonging to some set A. So note that there are two variables. It is closed and convex with respect to x, and nothing is said about y, and y belongs to some set A. There is no condition on A. Then consider the function g of x equal to max over y in A f of x, y. So the result is that g, which is the pointwise maximum of f over y, is convex in x. The result is an interesting example since here the function g is not in explicit form and is specified as the output of a maximization operation. Further, if you could have solved this maximization in closed form, verifying if the resulting function is convex or not would have been easy. But we are looking at the general case when g cannot be found in closed form and has to be written implicitly using the max operator. So how to show that g is convex? First, g need not be differentiable, so we cannot use the first order or second order conditions. For this case, however, epigraph based definition will work better. So let us try to check if g is convex by calculating its epigraph. The epigraph of g is the set of all x, t such that max over y of f of x, y is less than or equal to t. Now what can you say about this inequality? In general, whenever you have an inequality of the form max of some numbers less than equal to t, it follows that all those numbers on the left hand side have to be less than equal to t. So the inequality translates to a bunch of inequalities, one for each value of y in A. So therefore the epigraph of g will be given by the set of all x, t such that f of x comma y is less than equal to t for each y in A. Note that we did not put any restriction on A, so A can even be a discrete set. Equivalently, we can say that the epigraph of G is the intersection of the epigraphs of f seen as a function of x for a given y over all y in A. This is because each inequality of the form f of x comma y less than equal to t can be used to define the epigraph of f with respect to x for a given y in A. Because you can have multiple inequalities, they all translate to an intersection of each of these sets. So to summarize, the epigraph of G is the intersection of epigraphs of f over all y in A. Now the final step, which is that since f is given to be closed and convex for each y in A, it follows that the epigraph of f for each y in A is also closed and convex. The intersection of multiple closed and convex sets is also closed and convex, implying that the epigraph of G is closed and convex. Therefore, we conclude that G is closed and convex function. So in this example, we see that the epigraph definition of convexity may sometimes be more useful than the others, particularly when establishing general results. As an aside, I wanted to make a comment on the term supremum. The supremum of a function f of x is defined as the smallest m such that f of x is less than or equal to m. You might have seen the definition of supremum for sets. We can also use that definition by calculating the supremum over the range of the function. So how does the supremum differ from the maximum of f of x? The two are equal if f of x is equal to m for some x. If a function has a closed domain and it is continuous over that domain, then from the extreme value theorem, the supremum of the function is equal to the maximum of the function. However, if you are dealing with discontinuous functions, it could happen that the range is an open set. Consider, for instance, the function that jumps from 1 to 2, but it is continuous from the left. Since the function does not take the value 2, its range does not include 2. The smallest m, such that f of x is less than equal to m, is still 2, but in this case the maximum is not defined. So there is this distinction between supremum and maximum. Another scenario is when real valued function is unbounded above and therefore has no maximum. Example of such a function is x square. But since we are comfortable dealing with infinity, we can say that the only m such that f of x is less than equal to m is m equal to infinity. Note that f never actually attains this value, so infinity is not really the maximum, but only the supremum. Since supremum is more general, we can safely say that we will always use supremum. But the convention that we follow is that we will write it as max. In other words, we will define max to be the supremum and use it everywhere. So we are basically voiding the original definition of max and redefining it as supremum. So henceforth, max and supremum will be same. Notwithstanding the subtle distinction between supremum and maximum, these are immaterial in practice, especially when dealing with numerical methods. The computers only calculate things to a certain precision, and numerical algorithms do not differentiate between strict and non-strict inequalities. So it does not matter if you do not understand this distinction, at least in practice. The entire distinction is largely academic. Before concluding, let us take a look at an example. Consider a function in Rn which is the maximum of all its entries. That is, pick the largest entry of the vector x, and that is the value that function takes. You can write it as max over I of xi, and equivalently as max over I of h of x comma I, where h of x comma I is the function that takes the vector x and integer I as inputs and outputs the ith entry of x. As you can see, for each I, the function h of x comma I is a linear function of x for a given I. Hence, h of x comma I is closed and convex. It follows therefore that the function f of x is also closed and convex. So that is all for this video. We'll continue with conjugate functions in the next video.